So the next challenge is how do you store hydrogen? Hydrogen is a problem because the molecule of hydrogen is so small that it's very easy to have leaks with hydrogen. And the Department of Energy had set some goals. These were the initial goals for the program. Being able to store hydrogen under these conditions of a specific volume. These are kilograms of hydrogen per square meter, and this specific weight. If you liquefy hydrogen, this is what you get. Your specific weight is pretty good. Your specific volume is very good. So liquid hydrogen is actually, you can put a lot of energy stored in liquid hydrogen. This is why it's so attractive. Look at diesel and gasoline. I mean, this is, if somebody asks you, why do we use diesel and gasoline for transportation? Right there, okay? When you look at the specific volume and the specific weight, nothing beats diesel and gasoline. This is the reason why we use internal combustion engines. The amount of energy stored in these fuels is incredible. I mean, this is not an accident. The reason why we depend on fossil fuels and we use diesel in particular is that the specific volume and the specific weight is very good. There is so much energy stored in those fuels, and you can store them in a relatively small amount. Obviously, things that beat fossil fuels are nuclear power. I mean, with a little tiny amount of uranium, you can probably beat this, but this is the reason why for transportation we use diesel and gasoline. These specific weight and specific volumes are remarkable. So one of the goals of the program, the Department of Energy program, was to being able to store hydrogen in a way that at least will get up here, still be short of liquid, the liquid condition. And there are some concepts. For example, there is something called metal hydrides that can store hydrogen inside the crystalline lattice of the material, okay? And there is a lot of work with these systems. You can use carbon nanotubes to store hydrogen. There's a lot of interest in using carbon nanotubes as a way to store hydrogen. You can store hydrogen under high pressure. Now, the pressure is not going to be high enough to liquefy it, but this is what most people are doing today. You have these tanks, and I'm going to show you here those tanks in a minute. Those tanks are made with composite materials, and they can sustain pretty high pressure. And then the goal, and actually this goal was met, was to further increase pressure. We're talking about 10,000 psi of pressure, and you will need to use composite materials to be able to withstand these very high pressures. Actually, let me show you. We're going to come back here in a minute. Let me show you, because this connects with the conversation we had yesterday about composites. So these are the slides that show how people are building tanks to store hydrogen. Okay? Do you remember the conversation yesterday about composite materials? Somebody asked, the robot with the fibers and all that. Sorry, guys, you missed that one yesterday, but we talked about how to make composites. You look at these cylinders. You see this orientation? Okay. Now, this one, somebody mentioned the bending problem that you may have with the tanks. Well, this takes care of the bending, and then on top of this, you're going to have fibers going in the circumferential direction. And those fibers are going to take care of the hoop stresses that are going to exist when you have pressurization. This is the dome, the caps of the tube, but it's all about carbon fibers, okay? And this process called filament winding, where you can make these fairly large tanks. Everything is automated. This is a robotic arm that applies the fibers, again, in prescribed conditions. Somebody sat in a computer and calculated the stresses, and they said, we got to put fibers in the 0 degrees, 45 degrees, 30 degrees. Okay, and these are more detailed. You can see how the fibers get surrounded. And then the idea is that every automobile is going to have one of these tanks to store hydrogen at 10,000 psi. Now, that doesn't get you where we would really like to be. When you compress hydrogen, you have very specific weight. Your specific volume is still relatively low. And the consensus is that to get to these values, it will require a lot of science. And there's a lot of work trying to look at these solid state approaches to store hydrogen. And this is probably going to be the answer. So we haven't gotten there yet, but this is going to be important for the future because every car is going to need to store hydrogen enough to give you 300 miles or 400 miles of driving range. And one of those solid-state methods involve, I mentioned these carbon nanotubes where you can store hydrogen, hydrides of metals where you can store up to 5% hydrogen in the crystalline lattice of the material. There are some systems based on sodium and boron where you can store hydrogen, and with a little bit of heat, you can release the hydrogen. So there is a lot of work, a lot of research going on in this area because people really believe that hydrogen, and especially fuel cells, is going to be the way of the future. And the whole idea with hydrogen, again, is that you can use it as a fuel, but more importantly, it can be as a way to store energy. Let me show you some slides of what people see as the future of transportation. You would like to use hydrogen to drive for at least 300 miles between chargings. You should be able to accelerate very fast. The engine should last for at least 150,000 miles. The cost of the system has to be $50 per kilowatt, which is a very aggressive cost. And once you meet all these conditions, you're going to be able to compete. So this is the objective of these programs that BMW has in Southern California. Demonstrate that with fuel cells, you can get into that area. This is what a fuel cell, these were made by General Motors in Ballard in Canada. That's what a fuel cell looks like. And then that fuel cell will be moving an electric motor. The nice thing about electric motors is that they are very efficient. You know, the efficiency of electric motors is very high. But you will be driving these electric motors with those fuel cells. Every electric motor has magnets, okay? And the problem that we're going to talk about tomorrow is that a lot of these magnets contain neodymium, which is a rare earth element, and the availability of those rare earth elements has become a problem. So one of the areas of research in which we are involved is trying to develop magnets that do not contain rare earth elements. So that's an area where we are doing some work. And then the main objective is going to be for electric motors. And not just for automobiles, but if you think about it, every wind turbine has a generator, and the generator also needs magnets. So this research on magnets is not just for electric motors for automobiles, but also for generators in wind turbines. You have a lot of mechanical engineers trying to decide how the car is going to be built. One approach is that you're going to have these tanks storing hydrogen in the chassis in the bottom of the car. You're going to have your fuel cell here. And in some designs, you have one electric motor, but there are some cars that have one electric motor per wheel. So you have 4 electric motors, and then you have a way to control the motion of the electric motor. It's like a 4-wheel drive pretty much, where you have one electric motor per wheel. All the energy is coming out of the fuel cell, and then the hydrogen is going to be providing the fuel to the fuel cell. People are very concerned with hydrogen, and this is why safety is so important. If you're going to be putting hydrogen at 20,000 psi, that's a lot of energy. And this is not different from batteries. I mean, remember we talked about 5 things about batteries. What was the first thing that we talked about batteries? Safety, you know. Safety, safety, safety. And the same is true about here. The last thing we want to see is a tank exploding and killing a family on a highway. I mean, the amount of energy that we're dealing here is pretty substantial. And this is where, you know, one area, and I don't know if you talk about this at the university level, but the area of ethics, you know. Engineers and scientists have a moral responsibility to work in products that will not damage the public. And sometimes to make a profit, companies, sometimes they don't pay a lot of attention to safety issues. And I think it should be mandatory. Every student that pursues a career in science or engineering should take a course on ethics to make sure that, you know, whenever you go and work for somebody, that you are not going to sign on a product that could endanger the public. It's a tremendous responsibility, guys. Same thing when people who are making boilers. Every time you work with pressurized gases or electrochemical systems that have a lot of energy and the ability to release a lot of energy very fast, there's always going to be a danger. And we have to be aware of that, and that has to be a responsibility for all engineers. So this is a typical concept for a future car that will be relying on hydrogen. And again, a lot of energy here, and something to be concerned about. So we talk about that. We talk about the tanks. And then in the future, you should be able to pump hydrogen in no more than 5 minutes, to fill a tank in 5 minutes. And that should be the goal for this system. So and then in the very future, and this is a very futuristic side, there is a philosophy that is a competing philosophy. Do you centralize everything, or do you distribute everything? So the idea of centralization is you have this big power plant that sends electricity to many places. The alternative version is that you have distributed generation, where each home could be independent of the grid. Now, there's always going to be a conflict of interest there. So if you have a company, a utility that provides electricity to a large area, the last thing they want to see is people producing their own power. Because people could sell their power. What sometimes people don't realize is that when the sun is not shining, if you don't have batteries, you better be connected to the grid to have electricity. And then the question is, who pays for the grid? Who maintains the grid? So one of the big decisions that we're going to have to make in the near future is, what type of rules do we set so that if you produce your own power at home, if you want to sell the power to the grid, you have to be invested in the grid. You got to put some money into the grid to maintain the grid and make sure that the grid is going to be there for you the day the sun doesn't shine, or the day somebody breaks your solar panels and you cannot produce electricity, okay? But the same is true about hydrogen. One vision for the future of hydrogen is that you will have a steam reformer right here in your garage. So you can take natural gas from a pipe. Most homes get natural gas. And then that natural gas, using this steam reforming, will produce hydrogen, and then you will use your hydrogen to power your automobile. Or in the future, you could use hydrolysis, okay, which will be more energy intensive but more clean, and you will use hydrolysis to produce hydrogen to power your automobile. And that will be a distributed model where almost each home will be energy independent. All you have to produce is fuel. You could have a fuel cell that will power your house. You will combine that fuel cell with photovoltaics, okay? But then again, it's an issue of economics. But everybody has to be vested in the future of the grid. Okay, let's make a pause there. Any questions? Any questions? And this business with hydrogen, people have been writing books about hydrogen for the last 50 years. And in fact, a very influential person wrote a book about hydrogen, and the title of the book was The Fallacy About Hydrogen. And this person was very critical about hydrogen. And he was talking about the need for a big infrastructure and all that. And people said, well, yes, you can see these big reactors. I show you these super cables distributing hydrogen throughout the country. But people say, well, you can do this in a more distributed way with a smaller investment, where each subdivision or a small community may be able to invest in a small-sized power plant to produce electricity, produce hydrogen. So I think the jury is still out. In the future, we are really going to know which argument wins. I think for big countries, it's going to be a combination of big central power plants and a lot of distributed generation. Smaller countries, if you are far on the outside in the countryside, distributed generation will make sense. In the cities, we're going to be a combination of both. So as long as there are financial interests, you're going to see a lot of options and lots of different technologies. Okay? Any questions? Is that clear?
You have talked about the liquid hydrogen.
Mm-hmm.
I think that the storage tank must be an open system, because if the hydrogen
Yeah.
and the pressure will rise. And
Bad news there, yeah.
so if you don't use the hydrogen, you are going to lose the hydrogen, no?
Yep. You know, the other problem with hydrogen, and this is something that people don't think about. When hydrogen boils, let's assume that you have a relief valve. Okay, most systems, if you pressurize a system by law, you have to have a relief valve. So every pressurized system, you need a relief valve to prevent an explosion. So if you have a relief valve with hydrogen, that hydrogen is so light, it's going to go up. And then the question is, will hydrogen be considered a greenhouse gas? And the answer is yes. So here we have again, you know, it's not simple, because what we've been trying to do is to reduce the emission of greenhouse gases. And we say, well, hydrogen should be clean. You know, you can produce hydrogen by electrolysis using wind turbines and solar. That's great. But what happens when you have a leak or you have a safety feature that you want to pressurize your liquefied hydrogen and goes up into the environment? The question is, will this contribute more or less than CO2? Or even things like methane. You know, there's a lot of interest. Methane is a more potent greenhouse gas than CO2. And you know, methane is a relatively clean fuel. But you know, if you look at the thermodynamic system as a whole, there are some issues with methane, especially leaks of methane. And we are drilling everywhere in the US to get methane through fracking, and a lot of that methane is going up into the environment. Cows, you know, when cows fart, they release methane. And that methane goes up in the environment. It's a greenhouse. So you are right. I mean, that's a problem with hydrogen. Unless you have a very complex system where you can collect it and recover it, but that's a problem. That's a good point. You know, I think the moral of this is there are no easy, clean solutions. You know, every problem that we have talked about this week is a complex problem. There's a technological aspect, there's a scientific aspect, there's a financial aspect, there's a safety aspect, and all these things come together, you know, and it's difficult to predict which one is going to win. But that's a good question, you know. As an engineer, we should always be looking at that. If it boils, it is going to expand, higher pressure, safety issues, to release the valve, what happens when, and then you look at the system at a larger scale, say, well, you know, it's going to be a greenhouse gas. We've been trying to fight this from the beginning, and now we are developing solutions that make the problem even worse than what we had before. It's not easy, guys. I mean, you know, I don't want to get you depressed because, you know, every action has consequences. Another example, in 2005, the US passed a law, and the law required the use of biofuels for transportation. And this was a political decision, because if you look at the map of the US, there's a region called the Midwest: Indiana, Illinois, Iowa, Nebraska. And these states are very famous for producing corn. Okay, they produce a lot of corn. And corn can be used to produce ethanol. So the senators and the representatives from these states got together and they wrote the law and said, some percentage of all the fuel that is sold in the US must contain ethanol. Okay? And they said, this is great. It's going to help the economies of our states. We're going to produce more corn. It's going to be made into ethanol, and then we send ethanol into the gas stations, and everybody's going to be happy. Well, guess what happened? The diet of an average person in Mexico depends on corn. I mean, tortillas come from corn. And what happened is that these are global markets for grains. So the price of corn went through the roof. There was no corn in Mexico to make tortillas because people were making money selling it for ethanol production. And poor people in Mexico couldn't afford tortillas. So the intentions were good. You know, ethanol is going to displace foreign oil, which is something that we want to do. But now you make a decision that has consequences that people hadn't really thought about. And there were riots in Mexico. I mean, the price of the tortillas went through the roof. Serious problem. So you see, you know, all these things are so interconnected. And talk about ethics, you know, as an engineer or as an executive in a firm, These are the type of consequences that we really have to think about. If we do this, what's going to happen? And one of the things that I will ask you to consider is make sure that every time that we have to make a decision, we don't mix things like water, food with energy. I mean, that's probably the worst mistake that we can make. And by the way, all these biofuels, they are so water intensive that people were diverting water for production of plants that we're going to use for fuel. If I have a cartoon there, I'll show you tomorrow. And in the cartoon, there is a mother, and there's a little kid on the table, and the mother is telling her son, eat your corn, because there are many hungry automobiles, waiting for the ethanol there. And that's a problem, I mean, there are serious consequences when we don't think about it. What else? Questions?
I have a very specific question
Mhm.
about electric
Mhm.
because most of the compounds you show, they operate with water.
Yeah.
And the question is, because you need to put electrolyte in some closed cell.
Yeah.
How do they make it like they cover it with glass because glass is consuming ultraviolet, and if people are using quartz, is it economically good or not? Because quartz is quite expensive to do.
Yeah.
Is there a solution for this?
And the solution to this is quantum mechanics. And half seriously, half facetiously, but for example, yeah, these the frequencies for these are on the short wavelength of the spectrum, but there is we have a lot of people doing quantum mechanics, trying to come up with alternative systems that will take advantage of other parts of the spectrum. And in fact, in the last 2 or 3 years, there have been some breakthroughs where people have looked at some very inexpensive, people at MIT reported last year, they have some compounds that are relatively inexpensive that could mass produce hydrogen using simple construction materials for the windows, for the vessels. Some of the challenges here is trying to make these things as nanoporous, so you have a lot of surface area, because at the end of the day, these are chemical reactions that take place between the surface and the water. So how do you make a mesoporous material that is also nanoporous? So there's a lot of material science and engineering, but the fundamental question of what type of wavelengths do you take, that's a quantum mechanics question. The nice thing about it is that we can predict just from gap band calculations what type of compounds should do the job. And then if you can tune these materials to work in a piece of the spectrum where the construction materials of the system are inexpensive, light can go through, then the better. But it's really, it's really quantum mechanics. And tomorrow we're going to talk about thermoelectrics, and it's exactly the same idea. You start looking at materials. Now, these are typical materials. Most of these materials occur in nature, and most oxides occur in nature. And there's so much oxygen in the atmosphere that these are fairly stable materials. But one of the advantages of having all these computational material science tools is that you could come up with a material that probably doesn't exist in nature, but it's just the exact material with the right wavelength that's going to allow you to use plastic windows to build these systems. So I think that's part of the research. Can we come up with the best material for the application?
But then titanium dioxide is doomed from the design, from the beginning, because it's so popular in water splitting. And but by design of the cell, it is like.
Yeah, and the workhorse in this is titanium. This is the most widely used. And these are fairly abundant materials. Tomorrow we're going to talk about critical materials, and we're going to see some materials that we should avoid at all costs. Titanium is not one of those, but there can be some band gap engineering where you could even use some of these base materials. You can dope them just to shift the spectral characteristics of the material. But it's all about quantum mechanics. If you can really understand how the electrons behave, that's 80% that's really 80% of the problem. More questions? No, very clear? Everything very clear?